Alright guys, so today we are understanding series and sigma notation. So basically we're going to look at some sequences and then we're going to do some math. Okay, so to go to 2 to 4, 4 to 6, 6 to 8, we are adding by 2 each time. So my next two terms would be like 10 and 12. To go from 2 to 4, 4 to 8, then we would go 8 to 16 and 16 to 32. Because on this one, we're multiplying each of these guys by 2. Here, we're keeping the 3 on the top, and then to go to 4 to 8, 8 to 16, we'll multiply by 2. So 16 will be 32, and then 64. So on this time we're multiplying by 1 is staying on the top because I'm not changing my 3, and then I'm multiplying by a half because I'm multiplying by double on the bottom each time. On this sequence, to go from 28 to 24, 24 to 20, I am subtracting by 4. So this guy would be 16 and then 12. These series or sequences are arithmetic or geometric. So arithmetic are the addition and subtraction type, so addition and subtraction, and then the geometric are the multiplication type. And I'd say multiply and division, but we're really not dividing, we're multiplying by a fraction, which helps us make smaller numbers, right? So geometric sequences is multiply. Now of the two, there is a change every single time, and for arithmetic, we call that the common difference. And for geometric, we call that the common ratio. So again, these are how much it's changing each time. Okay, and it should be a constant change. For example, we are adding by 2 on this one. So if I added by 2 here and then I added by 4 here, that would be a difference of changing, right? Like it's going up by a little bit more each time. And the same thing with multiplying. If I multiply by a half here and then a fourth here and then a 16th here, like then it's changing as well. So it needs to be a constant change all the way across your sequence. And then we can get these formulas. And we talked about these in secondary 1. So we have the arithmetic explicit formula and the geometric explicit formula. So this D is our common difference. And this is a linear equation. The geometric is an exponential curvy, and the R is your common ratio. So to figure out the common ratio, you could take the second term, this guy, and divide it by the first term. And to figure out the common difference, you could take the second term and subtract it from the first term, which is what this business is saying right here. Okay, so what we're going to do is we're going to start by finding the explicit formula. And there's some other words here too to help you out. The explicit formula is also the general or the nth term formula. Okay, it's basically the rule for what's happening in the sequence. Now in this sequence we have a term that starts us. We call that a sub 1, the first term. Then this would be a sub 2, a sub 3, a sub 4. If we wanted a term before this, this would be a sub 0. So whatever term you write down is your first term. You can't write down your 0 term, but you do need it for your arithmetic if this is arithmetic. So here, to go from 2 to 4 to 4 to 6, this is just like we did on A, right? So for this one, we are going to be adding by 2 every time. That is our common difference. Okay, and now we can write our formula. So the way that the formula goes is I'm going to call it something. Well, I'm going to use a general term, a sub n, which means that any term in the sequence, if I know my first term, which I do, is 2, and then I know my n, which is my term number, and then I take away 1, and I multiply that by my common difference, which is 2, then I can figure this out. The reason that we do this is because, well, you could do it this way. Another way to do this would be having a sub n equals 2 and whatever our a sub 0 is. So our before term. the reason that I like this formula a lot is because then you don't have to think about the 0, the before term. This will just naturally give it to you. If you distribute and then combine your like terms, you'll get it. Or you can bypass this, bypass simplifying here, and just figure out the 0 term. So we're going to rewrite this equation up here. It's a sub n equals our first term plus our before guy, which is our y-intercept, basically, because this is a linear equation. So when we draw a linear equation, our line has to cross the y-axis right here. And where it crosses the y-axis right here, this is our 0 term. So this guy right here is our first term. So we need to go back one more so we can figure out where this y is crossing the x, or where the y-intercept crosses the y-axis. So if I go back here, my before term would be the opposite. So I would have to subtract 2, which would give me 0. So this would be, the formula for this guy would be a sub n equals 2. Oh, shoot. And we need an n here. A sub 1 times n. My bad, I forgot about that. 2n. You have to have a slope. Okay, and then you could do plus 0. This works out like that if you just use this formula. So you would distribute this 2, right? So you would have a sub 1 equals 2 plus 2n minus 2. These 2's are going to cancel, and now we have the same thing. A sub 1 equals 2n, like that. Okay? Anyways, I don't really care which formula you use to get your actual answer, but you have to have a slope in there. Sorry, I forgot that for a second. Our explicit term is our first term times our common ratio, and then you have to do n minus 1, so that's what this business says. So let's do one of those. Let's do C. So on C, we figured out that what's happening here is we're going to be multiplying by a half. That's our common ratio, our R. So a sub n equals our first term, which is 3/4, times our common ratio, which is a half, and then we do n minus 1. So that means if I picked a term number like 15 and then I plugged it in here, I could see what the 15th term of the sequence is. And the same goes for this. That's why these explicit formulas are so nice. Anyway, moving on for a sec. A series, so what we're going to switch now into is like a series. So a series is the sum of the terms in a sequence. So we just use pluses, addition, that's a weird word to say, instead of commas. They're a finite series and something else series. What did I write? Oh, infinite? Yeah. So finite means that it ends. Infinite means that it keeps going. So we're going to see if we can tell which is which. Okay, so this guy here, each time from 1 to 3, 3 to 5, 5 to 7, our common difference is 2. And it stops, right? So this is going to be a finite. This one here, this one is going 1 to 2, 2 to 3, 3 to 4. So we are adding by 1 every time. That's our common difference. And this one is an infinite series because it doesn't stop. And the same with this guy, it's going to be an infinite. But this time we're multiplying, right? So our common ratio would be multiplying by 2 because our number's getting larger. Okay, so here's what you've been waiting for. So we use this capital E. It's called a sigma. It's a Greek letter. And that is going to mean to add all of the things in our sequence. So we're going to add term numbers. Now, this number, whatever's on the top of our sigma, is when we stop adding. Our formula goes here. So that would be like this that we wrote down. This guy is a formula. And then this guy is a formula. So if we have an exponent, it's geometric. If we don't have an exponent, it's arithmetic. Okay? So our formula goes here in this cute little spot. And then this is just saying where we're going to start at. Okay, and usually we start at 1. So we're going to expand this guy. So we want to go 5 terms. We're going to start at 1. So what we're going to do is we're going to just plug in 1 to our k because it says k equals 1. So we have 2 times 1, oh crap, plus negative 1. And then keep going. 2 times 2 minus 1, 2 times 3 minus 1, 2 times 4 minus 1, 2 times 5 minus 1. Okay, so 2 times 2 is 2 minus 1 is 1. 2 times 2 is 4 minus 1 is 3. 2 times 3 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. And 2 times 5 is 10 minus 1 is 9. Okay, so now we need to add them together. So we're going to add 1 and 3, and 3 and 5, and 5 and 7, and 7 and 9. And that will give us our sigma answer. So when we add all of these together in our calculator, then we get 25. So 25 will be our answer. Okay, now sometimes, like this guy, this is an infinite, right? So that means that we're not going to be able, like, to stop adding. It's going to keep going. So, anyways, I'll talk about that in a second. On this side, we're going to expand these guys. So we want to go 6 terms. We're starting at 2 this time. So we have 3 times 2 plus 1, and 3 times 3 plus 1, and 3 times 4 plus 1, and 3 times 5 plus 1, and 3 times 6 plus 1. So we got 7, 10, 13, 16, 19. So 65. Okay, that's our answer. And then this one, you would do the same thing, but this time it's exponential. So we would have 3 squared and 3 cubed and 3 to the 4th and 3 to the 5th. So we've got 9, 27, 64, 81. Dang it, I was going to say 81. 243. And then we add 9 and 27 and 81 and 243. And we get 360. Okay, now we're going to go backwards. We're going to write these guys as sigma notation. So we got our cute little sigma sign. Okay, so to go from 3 to 6, we're going to add 3. And then that keeps working, right? So we've got 9, so we have to expand this. Say that this 3 is going to be our k equals 1. So we have 3, 6, 9, 12, 15, 18, 21, 24. So that's 1, 2, 3, 4, 5, 6, 7, 8 terms. So then every time a sub n is going, so this is going to be where our sigma is. Each time it goes up by 3, each time. And if I went to a before term, 0, because 0 plus 3 is 3. So I don't need this, I don't need this. So we just put 3n here. This is our answer. Or k. Oh, right, I used k here, so I'm going to put a k here. Sorry. Yeah. So you do the same thing on this one. So to go from 4 to 16, we're going to multiply by 4. And we've got 64, and 64 times 4 is 256, and 256 times 4 is 1024, times 4 is 4096, times 4 is 16384. So we've got our sigma k equals 1, 1, 2, 3, 4, 5, 6, 7 terms. And then our explicit formula would be a sub n equals our first term, which is 4, times our common ratio, so it's getting 4 times larger, and then n minus 1. So this would be our formula. And if you needed help remembering how to write it, it's on the front side. I'll review. We don't need this guy. This is where our sigma goes. So we have 4 times 4, and then we're going to use a k because that's what our variable is here, minus 1. So this is this guy. Let's see here. Okay, then we're going to use the calculator to figure this out. So I'm going to show you how to do this really quick on our calculator. So on this cute little calculator, you're going to press math, and then you're going to go down here to sum, and look, it's right there. Isn't it so cute? So then you type in this business, 5, you get an arrow up to 20, and then what have we got? 2, but not k. See, it says x equals 5. So on your calculator, where did you go? Right here, you got an x. Right here, next to the 4. So you can't see it right there, that button. X minus 3. Here we go. That's the answer, 352. So we use the calculator to find the sum. So the calculator figured out what each of the numbers in the series is, and then they added them all together. But this is a different calculator, TI-83 or TI-84 graphing calculator, and we don't use that. So this stuff is not helpful for us. So you go math, and then you scroll down till you get sum, and then you see this and you press enter. Really easy. Same thing, it doesn't matter if it's geometric or arithmetic. So let's just do D really fast. So clear. Math, scroll down. There it is, 5. Oh, here, we can write that there. 5 is sum. You could even type 5, it'll like click you right over. Okay, sorry, lots of back and forth. Okay, then it's 1, and then up top we got an 8. Over here, -2, and then I'm gonna use my fraction-y boxy button because we have it, so let's use it. Oops, delete. Exponent x. There we go. Now this guy looks like that guy, and we get, oh, it's so nice, -255 over 128. Now sometimes these guys, the fractions are too big, so if they spit out a decimal, you can put that there too. Okay, if you guys get stuck or you need any help, let me know. Have a great day. I hope you have a fantastic weekend. See you later. Bye, guys.